Okay, when we finished up the notes last time, we were talking about naming compounds and then their shapes. And what you have to do is you have to draw them so that they have their 8 electrons, okay? Well, the thing that's important about that is cells in your body recognize molecules by these shapes, all right? Molecules aren't flat, remember, they're three-dimensional. So they have, some of them have very complex three-dimensional structures like proteins, enzymes, things like that. So the Lewis structure, when we do a Lewis structure, we're drawing out where the molecules are. It's used to determine what their geometry is, what their shape is, okay? And to use that, they use something called VSEPR, which is valence shell electron pair repulsion. If you had chem last semester, you know what I'm talking about. But what it does is you look, after you draw your Lewis structure, you look at the bonding pairs and the non-bonding pairs, okay? So is there something attached? And we're just looking at the middle atom, the one right in the middle. Is it something bonded to that, or do you have a pair of electrons that don't have anything? If there's nothing bonded to them, those are called non-bonding. And then you use those to figure out their shape. The thing about them is they're going to separate as far apart from each other as possible. Okay, so here is a tetrahedral. You have one and you have 4 bonded to it. Okay, their shape, they're going to spread each other out and they're going to be what they say 109 degrees. Okay, so that's when you have 4 bonded. When you have 3 bonded to the middle and no lone pairs, okay, they're going to be 120. So they're going to spread out a little bit farther because they have a little bit more room. When you have 1 in the middle and 2 bonded to it, okay, no lone pairs, that's linear, okay? So these are 3 of the shapes. So this is where you've got 1 in the middle and 4 bonded to it. That's tetrahedral. When you have 1 in the middle and 3 bonded to it, and again, now we're talking about no lone pairs, that would be trigonal planar. And then when you have 2 bonded to it, no lone pairs, that's linear, okay? All right, so electric geometry, okay, VSEPR, it helps you predict the shape of the molecule. And again, it's important when you have a substance that a cell needs to recognize. So when the central atom has only bonding electrons, no lone pairs, like I was saying, no non-bonding electrons, the molecular shape is either going to be tetrahedral, trigonal planar, or linear. Those are the 3 shapes. Now, when you start throwing in lone pairs, which are non-bonding pairs, in other words, it's a pair of electrons with nothing attached to them, that changes the molecular shape, okay? Because that non-bonding pair, that pair of electrons, they have more repulsive force. So instead of staying spread out like they should, they'll squish them closer together, okay? So when you have, like, this is the chart where you had 4 with no lone pairs. That's tetrahedral. Well, if you have 1 lone pair, okay, these guys are going to get squished closer together, and that's called trigonal pyramidal. So it's like there's 4 bonded, but one of them is a lone pair. Okay, here's an example. Ammonia is one. You can see there's a lone pair here with nitrogen. So these guys get squished closer together. And then if you have 2 lone pairs, like water, okay, you've got one here and one here, they're called bent. Instead of being linear, they get squished together like this, okay? So if you have lone pairs, then you got trigonal pyramidal, if there's 3 bonded and 1 lone pair. If you have 2 bonded and 2 lone pairs, or even 1 lone pair as well, they'll be bent, okay? Here's another one. Here's the trigonal planar, like I was talking about, where there's no lone pairs. And then if you have 1 lone pair, like SO2, there's a lone pair here, okay? Now it's bent like it was before. Now you don't have to worry about the double bond thing, you guys. The double bond really doesn't affect it. The bond length is shorter, but it doesn't really affect the shape, okay? So here's trigonal planar, like with no lone pairs. And then when you throw in 1 lone pair, then you get that bent shape like you did with the other one, okay? So, and if you have 2 and 2, 2 bonded and 2 lone pairs, okay, then you're going to get different shapes as well. Here's one where there's 2 bonded to this, or 4 bonded to the central atom, that's tetrahedral. When you have 2 bonded to the central atom alone pairs, again, that's linear, okay? So these are telling you the shapes. And basically what you do is you draw it out and you look at it. Look at the guy in the middle, okay? This guy right here has 2 bonded to it and there's no lone pairs, that's linear. And there's a chart that tells you that, here, number of bonding pairs, 2, lone pairs, 0, linear. If you look back here, same thing. 2 and 1, bent. 3 and 0, trigonal planar. 4 and 0 tetrahedral, 3 and 1. So again, you're just looking at once you draw out your Lewis structure, and then you're looking at bonding pairs and non-bonding pairs, and that tells you the shape. Okay, so the shape of a larger molecule can be analyzed one molecule at a time. Here's a bigger one. This one would be, right, tetrahedral, and then you have another pair here on there, and that would be bent. Okay, so in this one, I'd say that the methanol part is tetrahedral because there's 4, and then the OH, the hydroxide, is bent because you've got one bonded here, or one here and one here, and then you got 2 lone pairs, so that's why it ends up going like that. Okay, all right. When you want to figure out what bond type you have, you can use something called electronegativity. Electronegativity is a measure of how much an atom wants electrons. Okay, what you do to figure out a bond type, I mean, generally can look and say, okay, I got a metal and a nonmetal, I know that's ionic. But if we're trying to figure out if it's covalent, we can tell if it's 2 nonmetals, but is it sharing its electrons equally, or is one getting more pull in the other one? And we've talked about this again if you've had chemistry before, but it's really easy to tell. What you do is you take their electronegativity and you subtract the difference between the two. The number that you get, if it's really close, if it's 0 to 0.3, nonpolar. In other words, they're sharing their electrons equally. You'll find them in the middle. Okay, if it's 0.3 to 1.7, they're sharing their electrons, but you'll find they're closer to 1 than the other. So they have poles. They have a positive end and a negative end. The best example is water. Water is a universal solvent because it has poles. It has a positive end by the hydrogen and a negative end by the oxygen. Okay, so they're sharing their electrons, but not equally. And then the last one, if it's above 1.7, then you know it's ionic. Okay, so the closer the valence electrons are to the nucleus, the more electronegativity negative the atom is. Okay, and again, if you look back here to the numbers, this is the highest right here. Okay, this is the lowest down here. You can see they're kitty corner from each other. These guys over here really don't want electrons. These guys over here really want them. So if I'm going to do a bond between calcium and bromine, I got 1 and 2.8. The difference is 1.8. I know it's an ionic compound. If I'm doing between nitrogen and oxygen, the difference there is 0.5. So that's a covalent compound, but it's a polar covalent because the difference is, bigger. Okay, so electronegativity increases again as you go from left to right, and if you go up the electronegative chart. So we're in the very top corner, again, you have fluorine. That's the most electronegative element. On the very opposite corner, you have the least electronegative. That's cesium, okay, and francium. I guess they're both the same. So a polar covalent bond exists when the atoms have a difference in their electronegativity. In other words, you'll find the atoms, the electrons, the bonds, closer to one end than they will the other end, okay? And those are called polar bonds because they set up poles. They have a positive end and a negative end, okay? So they're sharing their electrons, but they're not sharing them equally. And they use an arrow that points. It's called a dipole. It goes from the positive end to the negative end. So they draw a little arrow, okay? And that is showing you which way you'll find the electrons. Okay, here's an example. This one is sharing them equally, so this would be nonpolar. This one, they're closer to one end than they are the other. Okay, so this one would be one pole, the negative end, and this one would be the positive end. Okay, so when you're looking at polarity with more than one polar bond, they can be polar, nonpolar. So in other words, you can have one polar bond and one nonpolar. Here's those arrows I was telling you about. Okay, carbon, this is the plus end, and this is the negative end. So if you were looking at carbon dioxide, this end would be negative and the middle would be positive. Those would be the poles. Here with boron trifluoride, again, it points the positive end. It's kind of nice because if you put that there, you'll think, oh yeah, this is the positive end. And this is the negative end. So these would be the poles. And here's carbon tetrafluoride, same deal. You can see where they go out. So the middle is positive and the ends are negative. Okay. Molecules with one or more dipole, like those ones I was showing you, it can change their shape a little bit because of those. But because the dipoles, they don't cancel out, you're going to end up with different attractions. Okay. But again, it's based on their electronegativity. You just subtract the difference between them and you can figure it out. Okay, so The other thing you look at when you look at molecules is the force of attraction between them. So like here, if I had two of these, okay, right now all we've talked about is the attraction in the molecule. But what about in between the molecules? Okay, because like when you have water, if you have a glass of water, you have hexillion number of molecules in there. So there's going to be a force between the molecules themselves, between the water. Okay, so excuse me. Intermolecular forces are found where there's like temporary connections between the molecules, and these forces can be broken. In the molecule, you don't break those forces unless you put them through a chemical reaction. But when they're just kind of together, they have electrostatic attraction, the positive and negative. Those are called dipoles, okay? When the positive end of water, the hydrogen end, is going to be attracted to the negative end of oxygen of another molecule. So you're going to have those dipoles. They're temporary sometimes they're permanent. It depends on the situation with the water, okay? There's also something called dispersion forces. Dispersion forces are really, really weak forces, okay? In a noble gas and in a nonpolar, it's the only force. So dispersion forces are found in every compound, okay, in between the molecules. But it's not a very strong force, okay? Dipoles are much stronger, all right? But these guys, the nonpolar molecules, aren't going to have any dipoles because, again, they don't have a positive and negative end. So they just kind of hang out. So this is a London dispersion force, or just a dispersion force, I guess. Here's a dipole. You throw in something with a dipole, and now these guys are going to be, they're not really affected by it because, again, they don't have a positive and an ended. So there might be a temporary, but it doesn't last. And here's some induced dipoles. So look at negative, positive, negative, positive. They're going to be attracted. These are going to be a much stronger force to hold those molecules together. Okay? So polar molecules participate in dispersion. Every molecule, every compound will have dispersion forces, okay? It's not a very strong force. Some of them will have dipoles. If they have dipoles, if they're a polar compound, they'll have dipoles. And dipoles are much stronger. And then there's a special kind of dipole, it's a hydrogen bonding. Hydrogen is a very small molecule. It only has one electron, so it forms a special dipole that's even stronger than a regular dipole. Okay, so you can have dispersion forces, which all compounds have. You can have dipoles, which are much stronger if you have a polar compound. And then you can have hydrogen, which is even a stronger dipole, but again, you have to have hydrogen. Okay, if you look at DNA, it has two extremely large molecular strands each side. You know, if you've heard of DNA is a double helix, double twisted strand. They have hydrogen bonds that hold the strands together. And that's a very, very strong bond, which is good because we don't want our DNA falling apart. Okay, so we finished. Yeah, sorry I was rushing a little bit there, but I wanted to get through. So again, that's talking about the shapes of molecules and, you know, the polar and the nonpolar and so on. So we are done with chapter 3. Again, there'll be like a little, after you go through these notes, there'll be a little review of chapter 3 for you to go through. And then next thing we'll talk about is chapter 4. So again, all of this stuff is just a review. Hopefully you already had it. I know a lot of you had chemistry last semester. If you didn't, you're going to have to do a little brush up, but you know, that's how it goes. So done with chapter 3.